Hi everybody, welcome back to Chem 161. We have a very exciting thing going on today, which is we're going to finish Chapter 3, finally. And that's really all I have on the agenda, so let's go ahead and get started so that we can get this out of the way. And maybe move on to a new chapter for, like, the first time in, 3.5 weeks? I don't know. It was before the exam. And that feels forever ago. This last section in the chapter is just a sort of segue between chapters. We're going to show how to make ions. If you've taken Chem 140, you know all about the Octet Rule. And, oh, I want everything to look like a noble gas. Well, we're going to formalize that here. We talked about how to form cations and anions by changing the number of electrons in the valence shell. For instance, if I wanted to work with selenium and figure out what ion it would form, I could manipulate its electron configuration like this. So here's selenium. And I can write out its entire electron configuration. I gotta find where it ends, though. Okay. There you go. So there's the electron configuration there. And what I can do is I can make it, say, if I wanted to make this selenium +2, I could just remove 2 valence electrons. So the valence electrons would be these two. So I could do that. Or if I wanted to make it selenium minus, for example, I could just edit this however I want to, right? So instead of 4 here, like it was originally, this would become 5. Now, at some point, when I start adding electrons in here, I'm going to have to put them over here, right? I can only hold up to 6 in the 4p orbital. That, with these two, will make an octet in the valence shell. This is where the Octet Rule term comes from. So there must be some limit to the number of electrons that I can drop in, and that limit's going to be based off of all the rules that we discuss in this chapter. So since electron affinity is exothermic and releases energy, and atoms typically want to be more stable, we can drop electrons into most anything, really. But how many should we drop in there? Well, we're going to drop in enough of them until we completely fill the valence shell. And what that means is that, let me get rid of this real quick. We'll just go back to what it was. The end result of that is that we are going to end up with an electron configuration that becomes isoelectronic with a noble gas. So, for instance, if I look at the nearest noble gas to selenium, and that's krypton. Krypton has this electron configuration. So it's argon, 4s2, 3d10, 4p6. So what I want to do is I want to make my electron configurations match here. So what do I need to do that? Well, I need 2 additional electrons, so I would do this to my ion, and this 4 becomes a 6. Excuse me. So what ion would selenium typically form? It would become selenium with a 2- charge, because it needs 2 electrons to match the electron configuration of noble gas. The noble gas is just the sweet spot between I can accept electrons versus I can hold electrons for nonmetals. Once I get to the noble gas configuration, adding extra electrons past that it's very difficult to keep them, because they go into an orbital that's too far away, like we talked about yesterday with electron affinity. But up until then, it's relatively easy. So all atoms are going to try and resemble noble gases by adjusting their electron configuration. Some atoms will add electrons and others will remove electrons. So there's selenium. Let's try doing this for barium. Now I'm going to need to use this screen here to do that. So we'll put that up there. I need to zoom in. Maya is in the background crying because I'm not hugging her currently. So let's look at barium. And I'm gonna write out the entire configuration for barium. No, I'm not. That's ridiculous. What I'm gonna do is I'm gonna do this. And you'll see why I'm doing this in a second here. 5s2, 4d10, 5p6. There we go. So there's barium. The nearest noble gas to barium is xenon. And we want to match it. So what ion should barium form? Well, if I want to match this, I got to get rid of these two. So the ion that barium would form would be 2+. So I would lose 2 electrons so that barium ends up looking like xenon. So our goal is to just match up our element with the electron configuration of a noble gas and adjust our charge by however many electrons we needed to either get rid of for metals or add for nonmetals. So now we can predict what any ion's charge will be. Now, there are exceptions to this, of course, and those exceptions are things like transition metals, lanthanides, and actinides. The reason that we have issue here is because we have d electrons, and the d electrons change your configuration so that it doesn't quite match. But what you can do is you could still just do the best that you can, and then you'll end up with an ion that's usually pretty stable. So what I mean by the best that you can is that, well, all of our noble gases have full s and p subshells. So if you have a few extra d electrons, that's fine. Just strip away all of the extra s electrons from the valence shell, and you'll get a usually stable ion. And this works a surprising amount of the time. So for instance, if I wanted to look at iron, and I'll just write its entire electron configuration out here. One, two, three, four, 6. There we go. What would be a common ion for iron? Well, I want a full S and P subshell. So I can do that here. That would just require me to get rid of this to do that. So if I did that, I would have Fe2+, and then my electron configuration would be and then I have a full S and P subshell in my octet. I can't spell octet. Oh, not octet. I'm sorry. Valence shell. That's not what I said. There we go. And the d electrons are kind of inconsequential, but you can also find reasons to manipulate those too. So, for example, iron 2 is very common. Now, if I look at my d electrons like this, and I go, well, having one of these paired seems kind of silly. Why don't we just get rid of that one and make this iron 3+? And iron 3 plus is also very common. In fact, it's the most common. So you can make a lot of rational arguments for all of these ions, but the first step is always going to be this one. Strip away all of the valence electrons so that you have a full S and P subshell. And either 1 or 2 electrons is going to go, depending on if you're in like group, what group is that? 6 or 11? Remember the exceptions when we were doing our electron configurations for the things like chromium and molybdenum and copper, silver, and gold, where you land on 4s2 or S2D4, for example. We have to move 1 electron over. So in those cases, you'll get rid of 1 electron. But in all the other cases, you'll get rid of 2. Now, as a result, you might be inclined to think, well, wait a second, isn't just 2 plus common for all transition metals? And the answer is, yeah, it totally is. You just get rid of the s electrons. And so nearly all of the transition metals will adopt a +2 charge to some extent. Now, some don't, of course, because of the exceptions that we talked about earlier. So, like silver is always +1. Like, it's impossible to find silver in any other form than +1. I don't think I've ever seen silver in a form that is not either silver metal or +1. Although I'm certain that it probably exists somewhere in some esoteric case. All right, so what I want you to do is I want you to predict from these 5 at the top here which ion you're going to always end up with by writing out its electron configuration. And then down at the bottom, play with the electron configurations for the transition elements and try and predict a common ion that can form. Remember, you need a full S and P subshell because that's what noble gases have. If you can get that in the valence layer, then you'll have a more stable ion. So try and predict what those are. And I just told you, like, they're all going to be +2, and one of them isn't. So just be careful. But predict the ions that occur for these elements. We'll go over the answers in about 5 minutes or so. All right, one more minute. We'll go over the answers here. All right, so what ions form for the following main group atoms? So fluorine, the nearest gas is neon. And in order to make neon or fluorine look like neon, we would need to do... Here is the electron configuration for... Sorry, squirting cats with water because they're being loud. Here's the electron configuration for fluorine. In order to make it look like neon, I would need to make it 2p6, which would make it F-. For magnesium, the nearest noble gas is also neon. And so here's its configuration. In order to make it look like neon, we'd get rid of these. And this would be the ion it forms. For cesium, the nearest noble gas is xenon. And the noble gas configuration for cesium is, I mean, we could just do this, right? Well, to make it look like xenon, dude, there you go. So this is the ion it forms. Arsenic's nearest noble gas is krypton. So there's what arsenic looks like. To make it look like krypton, we would need to get 4p6. So if we go like this, that would be adding 3 electrons. And you can see how this pattern is working by now, hopefully. So tellurium's nearest gas is xenon, nearest noble gas. And that looks like this. To get it to have a octet there, to match the noble gas configuration of xenon, we would have to give it 2 electrons. So there you go. For these bottom elements down here, if I write out their electron configuration, and then how many are for nickel? 8, right? Yeah. I want to have a full S and P subshell in the valence layer. So if I get rid of this 4s, I can then do that. And you can do that for all of these. Remember that copper's the weird exception because it ends up being 4s1 3d10. Now, if you want to predict more than one for some of these, you can start playing around with, like, looking at the d electrons and seeing, okay, can I unpair them? Can I get rid of all of them? And make predictions that way. We're not going to go over that because there's just too many possibilities, and it's not really worth memorizing these at this point. But you can do that. All right. All these ions that we just formed, these are called monatomic ions. So anything like this, or this, or this, or that. These are all monatomic ions because it's just one atom that we have changed the number of electrons on so that it is no longer the same as its protons. Now, at the very beginning of the chapter, I showed you the list of polyatomic ions. Actually, they might have been in chapter 6. I don't remember. That was so long ago. In polyatomic ions, we've bonded a bunch of atoms together, and then we changed the total number of electrons available to create an ion. So a polyatomic ion would be something like this, or say this, or that. Functionally, these ions work the exact same way in terms of their charge as monatomic ions do. So when we make ionic compounds out of these, we can just look at the charge and not the identity of the atom. Now, if I wanted to look at certain characteristics of the molecule, all I do is just add all of those together, or multiply if I have the same thing. Like if I was doing molar mass, you would just add all the molar masses together. If I was counting electrons, I'd just say, oh, okay, I have 3 of these times 7 electrons each. You multiply them together. No problem there. Sorry, just check the chat. You don't get the copper rule. So the copper rule is an exception. If you land on D9, then what we observe is that this is the configuration. So if you recall that anytime we land on D4 or D9, we move 1 electron from the s orbital to the to the d orbital. It's just what we do. So with copper over here, you would say, oh, I want a full s and d subshell. So I'm going to get rid of this electron, and that's why there's only a plus there. Because we only got rid of 1. The same thing will happen in the chromium column and the other atoms in the I can't speak today. The copper, silver, gold column. They do that too. Yeah, pretty much everybody in group 11. I can't see the numbers on my table because it's like halfway under my desk. Here we go. Yeah, so group 6 and 11 is where you see this. This slide is just talking about counting electrons. So if I had N3, I would have 21 electrons because there are 3 nitrogen atoms together. But putting this extra electron in here would increase this number by +1, which is how we get 22. So you can count total electrons on molecules or polyatomic ions or whatever. Now, I'm counting total electrons here. Later on, this is actually important because a lot of people get confused by this example in the textbook. Later on, we're only going to be counting valence electrons when we're dealing with bonding. And so this is the total number of valence electrons, which we'll check out if you're reviewing your notes from later. After we've done chapter 4 and you're like, wait a second, this doesn't check out. This is confusing. It's because for some reason this specific example in your text counts total electrons. But the point is here that if you have a charge on something, it affects your total number of electrons, whether it's a molecule or an atom. This section is just talking about different types of bonds. We're going to explore bonding in Chapter 4 and 5. Chapter 5 is more just like advanced bonding rather than a new thing. We're going to do all of this in Chapter 4. The first type of bond that we're going to look at is the Ionic Bond. The Ionic Bond forms when you create a cation in some way and you create an anion in some way, and then those two attract to each other. We've studied how we create cations and anions extensively in Chapter 3. By looking at electron configurations, you can manipulate those configurations however you want to. In order to make an ionic bond, you have to have a positive charge so that you can attract it to the negative charge. What that means is that ionic compounds have to have either a metal that will get rid of its electrons, or it will have ammonium in it. So for instance, sodium, which is a metal, loses electrons to form sodium plus. And we can show why through its electron configuration. Therefore, it can be eligible to form ionic compounds, because ionic compounds require some sort of cation and anion. Now, how does this physically occur in terms of chemistry and reactivity? So if I have regular elemental sodium and regular elemental chlorine, do they react? And if you've seen this video from 140, it is the same video. Although I don't know if I have it linked here. I do have it linked here. So if you took 140 with me, you probably remember Lonnie from Lonnie's lab. Which I have to resize here. Oh, now he's backwards. That's no good. All right, there's Lonnie. Lonnie teaches at UC Berkeley, I believe. And he has this really creepy stare that just like looks into your soul, right? You can never unsee that. All right. So I'm going to show you the reaction of chlorine gas with sodium metal. So inside this container here, oops, I'm clicking on the wrong thing. Inside this container here, you can see when his sleeve is in the way there, that it's kind of yellowish tinted. That's chlorine gas. Chlorine gas is extremely hazardous and very dangerous, and you definitely don't want to breathe it. Now, you might think, well, why isn't it coming out of the container and Lonnie's exposed to it? Well, one, it is, but two, this vent right here is drawing air through in this direction very, 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 very quickly. So anything that comes out immediately gets sucked into the fume vent. What Lonnie's doing is he's cutting off of this block a piece of sodium, and the sodium is stored in a mineral oil. He's moving the sodium into this container, which has hexane in it, to rinse the mineral oil off, because mineral oil is kind of goopy and viscous, but hexane is very volatile, and it'll burn right off. All right, so the sodium is going to get put in a ladle like this, and then Lonnie is going to heat the ladle. The heating is to provide enough energy to ionize the sodium. And you could see that because of the color that the sodium burns right here. So if you remember from 140, whether you took it with me or not, you probably saw the video of Samita's. I'm trying to pause it on the color here. Where we heated metal cation solutions. And when you did that, they glowed a very bright color. And the reason that they do that is because the electrons in the ions go up and down through transitions. We're ionizing it. The result that you observe is the color. So we're providing enough energy for sodium to be ionized. If sodium gets ionized, then we can give the electron to chlorine in the tube as an electron affinity. And the act of doing that produces energy, which you see when we put these two things together. So the reaction is combining sodium metal with chlorine gas. By ionizing sodium to remove its electron and giving the electron to chlorine as an electron affinity. Now, because chlorine's electron affinity is more negative than the ionization energy of sodium, you get a net energy out. The atoms themselves lose the energy, and that energy is released to the surroundings, which can then be absorbed by other atoms to prolong the reaction. And this just keeps going until all of the reactants have been consumed. So what's in here is a gaseous sodium chloride, probably tinted by the color of the container, but as it condenses down, you end up with what looks like this. And that's table salt, which you can actually eat, and Lonnie is going to demonstrate that by eating in the lab, which is not appropriate. Bad, Lonnie, don't do that. No, don't eat in the lab. But this reaction does produce sodium chloride, which is edible. So this compound over here, the sodium that we started with, this element, sorry, very dangerous. It's explosive, and you don't want to touch raw sodium. The chlorine gas is extremely toxic. You don't want to breathe that. But reacting them together, you get sodium chloride, which is delicious. Now, to answer your question here, I think, won't you get half the chlorine as pure chlorine? What we'll actually do is we'll react one chlorine molecule with two different sodium atoms. There's nothing wrong with boiled eggs, but eggs are good in all sorts of forms, so. So here's the reaction that we did. So you can see that the elements are balanced. I'm using 2 atoms of sodium per molecule of chlorine. And what's going on is we're going to do something called electron transfer. I need to get rid of this electron in my sodium in order to attain an octet in the sp subshell to look like neon. So what I'm going to do is I'm going to take this electron and I'm going to move it over here to fill this sp subshell. I prefer eggs in the form of cake. That's a good form, I have to admit. So when I move this electron, both ions become more stable, because here's my noble gas configurations. I have full sp subshells in the valence shell. And I create the ionic bond. Now, all elements that react to form ionic bonds want to do this sort of strategy. They want to find the most stable configuration they can form, which is the full sp subshell to resemble a noble gas. And then as a result, those ions will then attract to each other, because now this has an opposite charge to this one, and they will be attracted to each other through electrostatics. So to form any ionic bond, those are our steps. Step 1, move electrons around until everybody has a full s and p subshell. Step 2, balance all the charges on all the ions you made so that the total charge is 0. Now here, I just needed one of each of these. But if I had something like, say, magnesium 2+ and chlorine, I would have to get another chlorine to balance out the charge. When we make an ionic compound, the total charge of all the ions summed together is always 0. Now, if it wasn't 0, and I put like a magnesium 2+ together with just one chlorine, the end result that I would get would be something like this, with a total charge of that. Well, it's still got a charge on it, so it's going to attract things that are negative, which would then change the formula, right? So the total formula charge has to be 0. Otherwise, things keep getting attracted to it, and it would not be stable. Now, as long as you know what ions form, and we do now because we know how to make the electron configuration for any ion, you can predict the formula of any ionic compound that I throw at you. So for instance, let's try and figure out the formula that would occur between magnesium and iodine. So first we got to write down the electron configurations. And then for iodine, we've got krypton. What row am I in? 5? Yeah. All right. So I need to make these all have a full S&P subshell in the valence layer. So here's my valence subshell if I get rid of these two. So magnesium would become this charge. For iodine, this would be my valence S&P full subshell if I did this to it. So this would become my charge. Remember, we want a full S&P subshell. These are all part of the same shell. All right. Once I've got a full S&P subshell in the valence shell, that's the ion that must form. There's my ions. If I put these together, the charges don't neutralize. So I actually need a second I minus to balance out the positive 2 of that. So now I have 2 positives and 2 total negatives. The charge balances. The formula would be, well, I got 1 magnesium and I got 2 iodine. MgI2. And I put this 2 here because I have 2 of these. And this Mg is just this right here. So we can predict the formula of any ionic compound by writing out the electron configuration and getting to the ions that form. Now, at some point, you don't need to write out the electron configuration anymore because you're just going to memorize this. Oh, it's magnesium, it's +2. Oh, it's nitrogen, it's -3. But until you can do that, write out the electron configuration and add or remove electrons until you get a full sp subshell in the valence layer. Remember this. This is how you know what ion forms, because all these ions are going to match the noble gas configuration. All right, so if I can make ions bind together to make a compound by balancing their charges, I must be able to do that with polyatomic ions because they have charges too. So no big deal there. You do not need to write an electron configuration for a polyatomic ion. You just need to go look it up, right? So let's determine the ionic compound that forms between sulfur and ammonium. So first thing we have to do is look up ammonium. And if you look it up, it's this. Then we have to figure out what ion sulfur forms. So there's sulfur. If we get rid of, not get rid of, sorry, if we change 4 to 6 here, then I have my full S&P subshell. I added 2 electrons, so this is the charge I form. So that means that the ions that I'm working with here are, I've got NH4 plus and S2 minus. Well, the charges don't balance out, so I need more of something. If I add another one of these, now the charges do balance out. So the formula I must have is 2 ammonia and a sulfide. So this would be the formula between ammonium and sulfide. Now, how iron rests, your description is correct, but it actually gives 3 electrons to oxygen. How would you know that? You'd have to do the experiment. So just as an aside here, so if iron gave 2 electrons, you'd get this. But if it gives 3 electrons, you get this. And it turns out this is the one that's much more common. For whatever reason. Alright, so I'm going to put some of these on the board here for you to try. What I want you to do is predict the formula that would form between each pair of elements by writing out the electron configuration. Once you know the correct ions that form from the electron configuration, balance the charges to make the formula of the ionic compound. Down at the bottom, I have thrown in some polyatomic ions. You'll have to go look those up if you haven't memorized them, which online class you probably haven't. It's fine. But I'm going to just write the formulas of those down at the bottom once we go over the answers. Okay? Go ahead and do this. We'll go over the answers in about 5 minutes, and then we'll take a break. So see you in a bit. How are we doing? Keep typing the answers in the chat as you get them. We'll go over the answers together in about 2 minutes or so. All right, let's go over the answers here. Yeah, just like that, Elon. I'm trying to find the right screen here. There we go. That's what I want. Sorry, Caitlin, I'm not sure what you're talking about. Can you be more specific? So, for sodium, this is my electron configuration. What ion will it form? Well, in order to get my full S&P subshell, I would remove one electron, and it would become sodium plus. Well, it would if I could write that. There we go. For nitrogen, I need this. In order to fill my SP subshell, I need to change this to a 6. So that means I needed 3 extra electrons. So the ions that I form are Na plus and not Na, N3 minus. Those are my 2 ions. How many do I need to balance out the charge? Well, this is currently what I have. I need more of the positive, so we'll go like this. Those balance out. My formula must be Na3N. All right. Now, we can do the same thing for each of these, but I'm going to skip the electron configuration part because you now know how to do this. So instead of writing all of the stuff out for cesium, I'm just going to skip straight ahead to this is the ion that you form, and this is the ion that you form for that one. Those balance out, so the compound that you make is cesium bromide. For magnesium and oxygen here, this is the ion that forms. This is the ion that forms for oxygen. Those charges balance out. So we just put them together. Same thing for aluminum and phosphorus, right? So aluminum will become this, phosphorus will become this. Their charges are the same, so they balance. There you go. So I don't teach the cross multiplication method because everybody does it and then they do it wrong. So this is the method that I'm going to teach. There are other methods out there, but what I strongly recommend is that you write out the electron configurations until you no longer need to do that and you have the charges memorized. And then balance the charges like this. How the heck do I balance a 3 plus and a 2 minus? Well, if we start doing this sort of back and forth thing here, these numbers change. And eventually you end up in a situation where they balance each other out. So sometimes this will take a little bit of work. And I'm making you do all of this work for an important reason. It's so that you can see how this works and bonds together. Can you just look at distance from a noble gas? You totally can. That's sort of where we're going with this. In chapter 4, what we're going to do is we're going to look at valence electrons and just count off spaces based on what group they're in. So if you're at that point where you're saying, oh, okay, well, I know which one this forms because I just count backwards to a noble gas. Yeah, that's what chapter 4 is going to tell us. This is why it happens, though. All right, and then for the last bit here, well, I ran out of space. So we've got ammonium and oxygen. Oxygen makes the O2 minus ion. This is ammonium. I need a second one of these. There you go. That's how that you write that one. I'm sort of scrolled off the screen there. There we go. We got barium. That's the ion it forms. Cyanide looks like that. I need 2 of them. There you go. And then for aluminum and chlorate here, here's aluminum. Here's chlorate. And then if I go down here and sum out the charges here, I need more chlorates, obviously. There you go. So now the charges balance. AlClO3, 3. Do the alkali metals and chlorine have anything chemically different from each other? There are chemical differences in terms of like atomic sizes and how they interact with biology. Like, for instance, if you have tasted potassium chloride table salt substitute, you'll definitely recognize there's a difference between the potassium chloride salt and the sodium chloride salt. Potassium chloride tastes way more metallic, so there's some sort of biological difference with how it interacts with your tongue and your taste receptors. And the end result is that salt substitute tastes terrible. What do we have? Magnesium and nitrate. So there we go. There's that. Not 3. There we go. And then by a similar token, I'm just going to write the answer to the last one here, because we're due for our break here. There's calcium phosphate. All right, so it's time for a break. Go ahead and pause the video if you need to look at the screen, because we're going to put this on the board here. And I'll see you in 10 minutes. I just got to find the music here. Hold on. There we go. Alright, we're back. Let me turn this down. Alright, so the last few slides of Chapter 3, thank goodness. We're going to go over all this together. We're not going to do the practice problems at the end because it's just kind of busy work. How do we differentiate between ionic compounds in terms of physical properties that we can observe? Ionic compounds are crystalline, they have very high melting points, and a common feature of them, which is not really mentioned in their text, is they are very, very regular looking. So if you can see, I'm drawing edges around the crystal here. You can see that you can find little cubes in your structure like this. Like these are all just edges of cubes. Here's another one. Here's one. And so on and so forth. You get these very flat, regular surfaces in ionic compounds and crystalline matter. So if you are looking at minerals and you see, oh, that looks like a bunch of cubes, like somebody didn't turn on no clip or something and all of the cubes clipped together, what you're looking at is an ionic compound almost assuredly because of how ionic compounds form. Since all of the ions are attracted to each other, so like I have opposite ions going in each of these, it makes sense to put my next ions in places where I would contact the most things as opposed to, say, here. Because this way I'm only contacting one thing, but here I can contact two. So we end up wanting to fill out the entire space before we go to the next layer. Because we would touch the most neighbors that way in terms of charge. So ionic compounds tend to form very cubic patterns as opposed to randomly arranging themselves. Because making a flat surface is more desirable. You end up getting all of your ions to be as close together as possible that way, as opposed to just stringing them all in a line and getting a random shape. Now, because ionic compounds are so tightly held together by these charges, they have really high melting points. Now, you can dissolve them by heating them up to an extremely high temperature, and I'm going to paste this link in the into the chat in case you want to watch it. We're not going to watch it because I want to get out of Chapter 3. I'm done with Chapter 3. So if you want to watch this on your own time, or even like right now, this is just melting sodium chloride with a blowtorch and showing that it conducts electricity, which is one of the next features, is that they conduct electricity if you melt them or if you dissolve them. So ionic compounds have these regular properties. We've tested their conductivity in 140 with the conductivity experiment that we did. Molecular compounds don't follow those properties at all. They're very different. We're going to talk about this a lot more in Chapter 5. Very, very briefly, it turns out, because Chapter 5 is not that long. If I give you a compound and you aren't sure, is it ionic or covalent, the best way to identify that it's covalent is to either look at its physical properties. So does it melt at a low melting point? Does it crumble? Is it not crystalline, etc.? Or look at the formula. If you see any metals or NH4, then the substance you're looking at is ionic. Later on, differentiating between these will be important, and that's why we're going over this. On the screen, you can see molecular compounds. I have put up a picture of water molecules. These water molecules are independent of each other. So, for example, this molecule right here is not interacting with this molecule in any way. Neither are these two. They are all independent of each other. They aren't connected to each other, not like ionic compounds. So that's why if you try and grind up sugar, you get this like really, really, really fine powder. If you try to do that with salt, it's a lot harder to get it as fine because it's still very crystalline. But sugar is not very crystalline at all. You can crystallize it into a crystal. But once you have powderized it, it's very hard to get it back to that. Now, covalent compounds have very low melting points relative to ionic compounds. For example, water is a low melting point. It's below room temperature. It's freezing point, right? 0 Celsius. Compared to table salt that melts at like 700, 800 Celsius, water's is quite low. Because they don't have charges, they don't conduct electricity at all. That's useful to know. Water is not a conductor. And yeah, that's really all I have here. So for this slide here, we'll just go over these together. Is this? Yay, there's the end. Okay. All this slide is asking us to do is classify as covalent or ionic, and really all you have to do is look for metals or look for ammonium. If you don't have those, then you're covalent. All right. Congratulations. It's over. Look at all the things we did. That's absurd. Yeah, it took us 3 weeks. No wonder this chapter is so long. So please make sure to review the chapter 3 content, because probably the worst part about finishing the chapter 3 is that there is a quiz on chapter 3. And it's 25 points over the entirety of chapter 3. Your screen will go blank before the next chapter pops up. I need to load the next slides. Never thought we'd get here, huh? All right. For the most part, chapter 4 is the last chapter. Interesting things that we will note here is that at the very end, there's a section from chapter 10 that I do. I talk about intermolecular forces. We'll do that real briefly. If we're really, really running out of time, I might skip it. I don't think that we will be, because we're just midway through week 8, so I have 2.5 weeks to finish this and then the one slide of chapter 5 or whatever. All right, let's get started. So the first section and what we're going to do today, we're probably going to get all the way up to 4.3 before we step. We're going to talk about just differences between ionic and covalent bonding. So let's explore how bonds work. So first of all, a bond is any interaction between atoms that hold them together in a molecule. Now, the very important thing to note is that the word here we're using is atoms. Later on, we're going to stick molecules together at the very end and consider intermolecular forces. But for now, anything that hooks two atoms together to form a formula unit or a molecule or whatever is called a bond. Now, we've already talked about ionic bonds. Here's our ionic bond. You need a cation to make the positive part. You need an anion to form the negative part. The attraction is what causes the ionic bond. So that's cool and all. Let's talk a little bit more about ionic bonds in detail. So I showed you the lattice on the previous slide in chapter 3. But you can see that if the chlorine is the green one and the sodium is the red one, that this chlorine is touching all the possible neighbors that it can. And there's even one inside the cube. And then when this next surface forms, or the next layer, it'll be touching the one that rests on top of it. Every ion tries to get into this situation where it can reach as many of oppositely charged components as possible. And so this is why the melting point is so high, because to remove one single ion, oops, hold on. That's confusing because it's the same color. To remove this single ion right here, I would have to break the interactions between all of its neighbors. Why does pure carbon create hexagonal lattices? We'll talk about that in Chapter 5, actually. At first I read that question, I was like, how the hell do I know that? I don't know that. Oh, I do know that. I teach that. Yeah, we're going to talk about that in Chapter 5. Why graphite is hexagonal and then diamond is tetrahedral. On the board here, I have the amount of energy that is needed to melt a mole of sodium chloride, 769 kilojoules. That's a lot. In fact, that's not just melt, but dissociate from solid into gaseous ions. Now, the term that we use in ionic compounds is not a molecule. Because all of these are interacting with all of their neighbors, it doesn't really make sense to say a sodium chloride molecule. So the word that we're going to be using from here out is called formula unit. A formula unit is just this. So a sodium and a chlorine from the ionic compound will be our formula unit. Where is it in the unit? I have simplified it by circling it this way. As we're going to learn in 162 possibly. I don't know if they teach solids in 162. I do. It's a little more complicated than that when we get to the unit cell. But for simplicity's sake, we could just circle any pair of sodium and chlorine and just say, oh, okay, I can copy and paste that to make the lattice. So that's going to be my formula unit. Now, what about covalent compounds? Covalent compounds don't have charges. The atoms instead share electrons with each other. So if these are my two atoms, so A and B, my electrons go between them. But because the electrons are shared and not transferred, there are no charges. That means that the bonding only really occurs in this orientation. The nucleus is attracted to the electrons that are shared, and the electrons that are shared are also attracted to the neighboring nucleus. So, unlike ionic compounds, which would propagate in all directions, covalent compounds focus their bonding between two atoms, and that's it. So as a result, you end up with independent units. And those units are what we call molecules. Now, covalent compounds, for our purposes, will form between only nonmetals. As an inorganic and an organometallic chemist, I can tell you that that's bullshit. Covalent compounds form in all sorts of cases, even between metals. However, for our purposes, we're sort of going to ignore that. Now, there is a common example that occurs, and that is the polyatomic ion, and we'll get to that in a little bit later. Now, how do covalent bonds form? Covalent bonds form when you take the orbitals, remember the orbitals that we were drawing the shapes of? If I have electrons that live in these orbitals, the way that I would make a bond between my two atoms is to overlap the orbitals. This is what's meant by sharing electrons, is that the areas in space where the electrons live are allowed to overlap. And in doing so, we form the covalent compound. Now, the reason that these overlap is to get a situation, here's my nucleus, I'll put the nuclei in the center, to get this plus minus plus sort of arrangement. So up here are my nuclei, and there's an electron floating around the outside here. In this circumstance, there's my electrons, they're between the two. Now, if I were to jam these even closer together, what would happen is that the nuclei would then be on top of each other, and that's no good. So the bond energy reaches a minimum potential well at some distance. Any closer and the nuclei repel. But any further away and the atoms don't see each other. So bonds will fall into this optimum distance. That is due to some amount of orbital overlap. We're going to talk about orbital overlap in Chapter 5 very briefly. But suffice it to say that the length of a covalent bond is dictated by this sort of Goldilocks principle. How much overlap do my orbitals do? And again, we'll come back to that in Chapter 5. Like we said earlier, covalent compounds are independent molecules. So water, for instance, if I draw its Lewis structure, and we're going to be drawing a lot of Lewis structures on Wednesday and then next week, all of my bonding electrons are between these two atoms and don't propagate in any other directions, so the molecules exist independently and do not form bonds with each other. Now, that's not to say that they don't form any sort of attraction, because they totally do. And we're going to talk about that attraction at the very end of the chapter. Now, an important concept that helps us define between whether something becomes ionic or whether something becomes covalent is this topic right here, electronegativity. Now, we've sort of defined metals as, oh, they want to get rid of their electrons. And we've defined nonmetals as, oh, they want electrons. And we can fill our electron configuration so that we get a full S&P subshell to look like a noble gas. That's great and all. But it turns out that for some elements, this is not as cut and dry. And remember how I talked about how elements in group 4A or group 14 don't really have a direction that they prefer? Like, we never did figure out what ion carbon forms, or silicon. I mentioned this in 140. I don't know if I've mentioned it in 161. But there are parts of the periodic table where you're kind of equidistant from either noble gas. Where will carbon go? Will it gain 4 electrons or lose 4 electrons? Well, it's the same, right? What should it do? And the answer is, it doesn't really do anything. It doesn't act ionic, or it just acts on its own. It does all sorts of different things. And the reason for that is because it actually has a rather high electronegativity relative to the metals, but a rather low electronegativity relative to other nonmetals. So it's kind of stuck in the middle. It doesn't know what to do. And so we get some unique results from that. So is there a region between ionic, where I just transfer electrons wantonly, and covalent, where I share electrons? And the answer is yes. Can electrons be shared unequally in a bond? Yeah, you just share them closer to one atom or the other. And so this is where the concept of electronegativity is introduced. On the screen, I'm going to show you this molecule. This is chlorine, Cl2. We're going to learn how to draw Lewis structures tomorrow. But what you can do from this structure is look at where all the electrons are. Each of these dots is an electron, and this bond is a pair of shared electrons here. Now imagine that those electrons were in a sort of tug of war, and that each chlorine wanted to pull the electrons towards its nucleus. Because the electrons are attracted to the positive nucleus, right? But there's a positive nucleus on the other side. So where do the electrons end up? Well, the answer is because both chlorines are exactly the same, they're both chlorine, the electron density stays roughly in the middle. So the electrons are not shifted in any direction over the long term. And it's because both atoms are pulling with the same strength. They have the same electronegativity. Now, in other words, where are the electrons? The electrons are in the middle. They're not always going to be in the middle because remember, electrons operate as wave functions. That's probability. We're most likely to find them in the middle. But we would say that the density is constant throughout the molecule. So the average is in the middle. Now let's do this. Does H pull on electrons as good as Cl does? And the answer to that, you should, of course, be saying no, because hydrogen only has one proton, right? If we calculate Z effective, I get 1 plus for hydrogen, but 7 plus for chlorine. Chlorine is going to pull way harder on the electrons, and so the electrons are going to end up closer to chlorine than they are to hydrogen. So the electron density is going to be more around chlorine, but the electrons are still shared. An example of this would be if you are sharing, like when you're a kid, maybe you're sharing toys with your younger sibling, but you get to keep the toys in your room. Technically, both of you get to play on the Nintendo Switch, but it stays in your room because you're older and more responsible, right? You're technically sharing, but you do have access to it more of the time. That's how chlorine is operating here. Chlorine is technically sharing the electrons with hydrogen, but it gets them more of the time. They are closer to chlorine. So, being pragmatic about it, chlorine is not sharing the electrons equally. This is not an equal distribution. But it is still shared. Now, why do specific atoms attract electrons to themselves more than others? It has to do with the quantum mechanics effects that we've already studied. So we referred to Z effective here, but we could also have referred to electron affinity, which involves Z effective, also involves N. And we could do this on a case-by-case basis for every atom on the periodic table. Let's look at its Z effective. Let's look at its N. Which one is most wanting to pull electrons towards it? And somebody already did that, and it was this guy. This is Linus Pauling. Linus Pauling is one of the most famous 20th century chemists and physicists because he contributed a ton of physical constants and research to the field of chemistry. It's a real shame that he is now known for going insane in his later days. The work drove him mad. He went on I don't know, I think it was a vitamin C kick or something, and he basically went insane. So that's Linus Pauling. We're going to use his work. We're going to remember him for his work and not what happened to him. Pauling devised a scale called the Electronegativity Scale. The higher an atom's electronegativity, the harder electrons are pulled towards its nucleus through covalent bonds. If an atom pulls hard enough, it keeps the electrons for itself, and the bond created is ionic. But if it can't pull that hard and the other atom pulls a little bit, then the electrons are forced to be shared. Now, we rate electronegativity on a scale from 0 to 4. 4 is the highest electronegativity, 0 is the lowest. No atom actually has 0, but we do have a 4 on the scale. Now, importantly, electron affinity is used to calculate electronegativity, but they are not the same thing. So this is used to calculate these numbers. That with Z effective and the maximum shell number, all of that gets put together and you distill out this chart. Now, if you look at the chart for the element that has the highest electronegativity, you find it over here. Fluorine is the highest electronegativity. Why? Well, it has a very high Z effective, and it's also very small. If you look at Coulomb's law, oops, not equals, but proportionality, if you make Z effective really big, and you make this really small, this goes way, way up. So the energy of attraction between electrons and fluorine is very high. Likewise, on the opposite side of the periodic table, we have elements that have very low electronegativity. And this is because they are very large atoms with very low Z effective. So electronegativity increases as you go up the periodic table and over to the right. Now, there are some interesting parts of the periodic table that occur. In the center here is what are called the noble metals. You might have heard this expression before. The noble metals resist electron transfer. Sorry, I was reading what was on the comment. I'll get back to that in a second. The noble metals have high electronegativity relative to the other metals around them. So iron, with its lower electronegativity, easily gives its electrons to oxygen or other things that want to take it. Oxygen is abundant in the air, so oxygen will corrode iron. But it won't corrode gold, because gold's electronegativity is too high. Gold is very capable of keeping its electrons from oxygen. And so it will not form ionic compounds with it, and thus it doesn't lose its electrons and corrode. The same is true for things like iridium and platinum. Silver is a little bit corrosive. Silver gets corroded a little bit, mostly in contact with sulfur, but oxygen can do that too. But these other metals in the center here, their electronegativity is just abnormally high. And the reasons for that are probably beyond the scope of my knowledge. They're definitely beyond the scope of this class. I could go look them up and probably understand it, but we certainly don't want to deal with more quantum mechanics here. We're done with quantum, right? The end result is that if I give you a periodic table, or you look one up online, then you will be able to predict the electronegativity of any two elements relative to each other based on their position. Now, does it make it really hard to bond fluorine with francium? Fluorine and francium should bond super, super easily. Because francium's like, oh, I really, really don't want this electron. And fluorine's like, yoink, it's mine now. Now, do I make a compound that sticks super well? Not really. There are other reasons for that. We'll talk about that in Unit 8, 9, whatever the thermo chapter is. Why are spark plugs made largely out of noble metals? For that reason. You do not want your spark plug to corrode because corroded substances don't conduct electricity well. And the whole point of a spark plug is to spark, right? So we make good quality spark plugs out of platinum because platinum resists corrosion. It won't react with oxygen in an environment that is both really, 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 really hot and also involves explosions and oxygen. So that's why spark plugs are made out of noble metals. All right. So this page just summarizes electronegativity, but this is really what you need to know. So if you compare any two atoms together, you can determine which one has the higher or lower electronegativity as long as one is further up or further to the right. Now, when we come back on Tuesday or Wednesday here, what we're going to do is we're going to start looking at different types of bonds and categorize them based on differences in electronegativity here. Although I am going to change this number. We'll change this number next time. We're going to categorize these as either covalent with no uneven electron distribution, covalent with some uneven electron distribution, which makes it polar, or this is an ionic compound. And so what we end up kind of with is a gradient here. So we have covalent and ionic, and our compounds are going to fall somewhere on this line. And where they fall, whether our bond is going to be more covalent or more ionic, is going to depend on the difference of the electronegativity, delta En. So that's where we're going to be going with this in Chapter 4, is we're going to explore bonding from this perspective of electronegativity. We're going to talk about polarity, and then we're going to start drawing molecules on Wednesday. So on Wednesday, we will... Oh, actually, no. On Wednesday, we're going to start doing nomenclature. So that's probably going to be the whole of Wednesday, is just... We're going to name everything. We're going to go through naming quickly, because we did that in 140. And then we'll get on to Lewis structures, and we'll be in good shape. All right. That's all I have for today. Thanks for coming out to the lecture. We will have the next one tomorrow. Next week is Memorial Day, so there's a holiday coming up for that. But the quiz for Chapter 3 will be due a week from today. Let's put that on the screen here. So, quiz for Chapter 3 due, and that'll be Tuesday, the 2nd of June. We're already in June coming up. That seems pretty soon, huh? All right, I'm going to go set that quiz to be published. I need to find this thing. There we go. Yeah, that's all I got. I'm going to try and get that lab video up tonight, maybe tomorrow, sometime this week. And we'll see you tomorrow for the next lecture. Take care.